That a shot? Okay. Well, we'll go ahead and do introductions, myself and Jessica. I know we also had a really wide variety of participants in this workshop, which is really interesting. So I encourage everybody to, if you can, flip on camera. And if we get to points, we'll stop often, perhaps to answer questions. Or Jessica and I were talking right before the workshop. This is our first time teaching this. We think that there's maybe some interesting discussion opportunities here for why do you do some of the things you do when you use this approach versus others. So we're covering a lot of territory in this workshop, and we're here to benefit you all. So please pause us along the way. We hear our voices all the time. We'd love to hear yours. And if we have some areas that we can provide some additional detail, we'd be happy to do that. Okay, I'm going to admit these last three participants, and the first part of the workshop is actually a little bit of a presentation kind of covering some of the background in terms of why does geography matter? How do some of these geographic information systems work? What are they for? And some examples of the type of work that I do in GIS, and Jessica will cover some of those on her own in the lab later. So if I got this right, I can go ahead and go over here, share this, do this. And does that just show on screen with just a single slide on it for everybody? Okay, great.
Yes.
So just quick way of introduction here. And again, pause this at any point in time, raise your hand if you've got questions. So my name is Matt Dunbar. I work at the Center for Studies in Demography and Ecology. I'm at the University of Washington. I know we cast the net quite wide for this workshop, and so we have folks both at the UW and further afield. So for those of you that do or don't know, the Center for Studies in Demography and Ecology is a research center. We're not an academic degree granting unit. We're a kind of a more broad research support organization in the College of Arts and Sciences at the University of Washington. We have over, close to 200 faculty affiliates and a large number of students that we support with research services, broadly speaking, from administering grants to statistical consulting, teaching workshops such as these. We have seed grants and computing resources, et cetera. So our purpose at the university, and what Jessica and I and many of our other staff really enjoy about our jobs, is we help people make their research better. So one of those areas that we do so is teaching workshops like this. They're free and open to the public. Students, staff, and faculty generally attend in pretty equal proportions, and it's a great format to get to know what we do here as well as learn something. And with all of my workshops, I like to point out this is just the starting point of the conversation. Jessica and I love hearing back from folks, whether that be, can we answer a question about what we learned in the workshop in the labs? Or I love what you showed me, but there's no way in hell I want to do any of that. Can I hire you to do that work? We're also here to be consultants and answer questions as well. So anything under the sun is within our purview. Okay, so with that brief introduction, I've been at CSDE since 2008. I got a PhD in geography from the University of Kansas, go Jayhawks, which will feature as an Easter egg for Jessica later in this presentation. And at CSDE, over my time here, I've also got to know a little bit of the inner workings of the center and all of our science core staff. So I help kind of lead the team, making sure that all of the right research scientists are getting paired up with all the right research projects here. So that's my background. Jessica, you want to tell us a little about yourself?
Yes, my name is Jessica Godwin. Depending upon how you count, I've either been at CSDE since 2022 or 2014 when I was a CSDE trainee and then a fellow myself. I got my statistics PhD from UW, from the stat department where I work with John Wakefield. For those of you at UW, you may know that he specializes in spatial statistics, and you may have even taken his class. If you haven't and you are a student, and you're interested in this type of work, I would like to advertise his spatial statistics class in either social science or spatial epidemiology, different kind of flavors of the same thing. If you're really serious about doing in-depth spatial analysis of data, we won't get into any of that today, but those resources do exist on campus. But obviously as a student, I learned quite a bit of that and TA'd for that class, but also a lot of my dissertation and my kind of favorite research problems end up involving small area estimation, where we're looking at summarizing some sort of individual level data at the area level. So this might be the county or the census tract, as we'll see today. So I do a lot of spatial data analysis, though I don't have any formal geography training. I do a lot of this kind of spatial data visualization and analysis, yeah, as part of my research. So.
Cool. Well, and you're in for a special treat because Jessica and I have been talking about doing this workshop for many, many years, and we finally put a date on the calendar. I don't know if we actually had time to do it right now, but we're doing it, and we're excited about it. And that is, the goal of this is to present to you all and get you kind of excited and started thinking about how you might incorporate spatial analysis in your own research. We're hoping to sell you on the fact that spatial data is maybe a kind of a unique beast in and of itself that requires some different ways of thinking about how you look at and display the data, how it's stored and structured, and the types of software or programming languages and packages that you use to analyze it. So today we're going to kind of dive in to just a couple of those and present two different kind of worldviews. But as Jessica and I have talked about a lot, they're really complementary. They're just different toolkits that you choose how you want to use them based on what you're most familiar with or what you're trying to accomplish. And like I said at the beginning, please stop and ask us questions, especially if you've got some ideas about how you might incorporate these in your research and would like to clarify, because I'm sure you're not the only person in the workshop that has questions similar to yours. Okay. So I'm going to start I've got about 15, 20 minutes of just some kind of introductory materials that will hopefully set the stage for some of our hands-on work that we're going to do later. So I'll do the slides, we'll take just a quick breather, answer some questions, and then I'll dive in and do a demonstration in a lab where people can follow along with ArcGIS Pro from Esri, which is a desktop GIS software package. Jess will do the same thing and have a little bit longer time to do a similar workshop in R. Okay. Cool. Okay, so as a geographer, I always have to convince people how cool geography is and that geography matters. There's always maps all over the place that kind of pique your curiosity and interest. This was just one that I pulled out of, the library of things that I've looked at over the years that kind of got me thinking we're part of a project that I was working on. And this has become more interesting because I went back last night to look at this map more recently, and the patterns and trends on this map have completely changed, and some of them within 5 years of when this map was created. So this is a map that's showing high school graduation rates by county in the US. Note the year is very important. I would have put it in the title of the map. We won't get into cartography here, but cartographers like to think about how quickly and easily it is to look at a map and understand what the heck's going on. I had to dig and find where's the data from and what are the years. But this is 2007 through 2011. So the US Census Bureau's 5-year ACS estimate. So kind of considering the time range. And then looking at the color coding on the map, we go from a low of below 50% high school graduation rates in the kind of darker orange, all the way up to in the dark blue, almost to 98, close to 100% graduation rates. And so why geography, or does geography matter? I guess I just ask you, do you all see patterns? Do you all see trends? Would you be able to sit down and kind of have a discussion about what you're seeing on the map? Maybe bringing to bear something about where you're from. I can look on this map and see where I was born, where I grew up, where I went to college, and probably have some hypotheses about those areas. But I would talk to Jessica about different regions of the map that I'm certain she would know much more about than I would know about Kansas if we're talking about the South. So guess this is just my segue to say, if you were to show all this data in a tabular format to someone, county by county, one, it would be really boring, but two, it'd be really hard to make any inferences about any spatial patterns or trends. But as soon as you put it on a map, color code it in this thematic map fashion, it really does draw some attention to some interesting potential questions that you might want to explore. Jessica, did you have some things to say?
Oh no, I just was zooming in and I can see, I'm from Alabama, but I'm from one of the very few blue counties in Alabama.
Absolutely. Yeah, very much. There's some spatial outliers. Texas was the one that over the years I always looked to and saw. And then I went back and looked at this. And in the next 5-year ACS, that entire band, that is the lowest color, had flip-flopped to near 100% graduation rates due to policy changes and an influx of kind of rules and regulations. So, yeah, spatial data along with temporal data overlapped allow for some really interesting analyses. So, this is where you would bring to bear the analysis and the statistics eventually to say why, what are we seeing? But a lot of what GIS offers for me is a way to get some sense of what are we looking at and the why. Okay, so you all believe geography is important. We're sold on that part. We can proceed. Okay, cool. So the rest of the workshop is just a quick look at what GIS is, Geographic Information Systems, some of the details about how that GIS software and/or programming languages or libraries get used, some of the things we consider in GIS, and then a few examples of some projects we've worked on. Okay. So what is GIS? Let's keep it really simple. GIS, Geographic Information Systems. We'll start in the middle with information. It's after lunch. Hopefully everybody had lunch, but maybe not dessert. So I just like this slide as a way to conceptualize kind of what we're doing in an information system. So data are that collection of kind of facts that you collect out in the world that are unstructured and are kind of raw information is not what a GIS is. A GIS is taking that data and information, taking that data and converting it to information by structuring it and asking questions of it that allow you to deduce some sort of outcome or pattern or structure in the data. So GIS, you feed it in raw data, but it is an information system for managing. And eventually, if you gussy it up for presenting that information, once you consume that, that actually translates some information, which converts itself to knowledge eventually. Okay, so the information system isn't just a data set with some spatial coordinates. The information system allows you to do something with that. Okay, I always challenge myself to include these little critters in my presentations to date myself. So what is an information system? This can be anything from just simple Excel spreadsheet. Example of an information system is kind of a SQL-lite, like Microsoft Access database, a full-blown SQL database, or I'm sure Jessica and R, there are different database structures as well that you work with. So the concept of an information system is a data structure and software package that allow you to work with that data type in particular that you're talking about. Here we're talking about spatial data. Okay. Microsoft Access is an information system devoid of spatial knowledge and structure. So geographic information is just adding on top of that a component, whether that be a set of software libraries or a software package that allows you to interpret the spatial nature of the data that you're looking at, display it, and as we'll be looking at later, run some particular forms of analyses, or as Jessica alluded to, there are statistical methodologies that can only be performed on spatial information. And so that's what's unique to a geographic information system, its ability to work with that spatial data. Okay, so geographic information system. So how does this work and what does it do for you? This is another one of these all-time favorite maps, and I like to look at this as a starting point to think about how we take tabular data, map it, and what that can do for us, okay? So a GIS allows you to derive information from any data with a spatial component to it. So there was a really wonderful crowdsourced data gathering endeavor that started years ago and it keeps going. And it was just based around this really simple question that I've got on the screen, which is, what do you call carbonated soft drinks? There's an online website that you can put this in. I'm going to go ahead and click on here, stop sharing here, share this browser window. Okay. So super exciting. It's a table of data. There's some fixed choice answers, pop, soda, Coke, or other. It's most popular, and then some people write in for other, and you can see what those are. Okay. But just looking at the tabular data, you might go find your own state and say, oh yeah, that matches with what I'm used to. But the real fun thing occurs when you go back and each participant provided their own zip code, so you can look at what county they're in. And this is changing over to the actual map here. Jessica, does that give me a thumbs up that you're seeing? Okay, I'll zoom in here. So this is a really unique symbology type, but the general gist of it is you can see the legend down here in the bottom left. Yellow is the county, stated that they call that stuff pop. Pinkish is Coke, and blue is soda. So information system allows you to take that raw tabular data along with information about the zip code for each of those responses and then map that.
This is really amazing. I think this is hysterical and really, really funny, or really fun.
Thanks. Yeah, it's always been that way, and it just continues to amuse me every time. And lots of stories I'm sure that can be told, especially the soda islands
Mm-hmm.
that exist. And like you said earlier, Jessica, you can find individual counties that what the heck's going on there? That in a sea of Coke, you call it soda or pop. Um, so fun map, but the point is this is kind of what a geographic information system allows you to see, right? Just looking at the raw state level data, you could present some sort of findings. County, you could run some analytical model, but the map and the exploration of the spatial data starts leading to other hypotheses that are really interesting. And then I'm sure, Jessica, you could probably create a model that would help explain how this came to be, population flows and migration that take soda namers from one part of the country to another, et cetera. Okay, so I'm gonna stop that share, get back to our presentation, hopefully. Okay, so how does all of this magic happen? So a GIS is basically a combination of two different kind of data types, one maybe that you're more familiar with and one that's new that captures the spatial information. So this is a visual representation of a really simple spatial data set that we would look at in a GIS. We'll look at something very similar to this in our labs in a moment, and that's just state boundaries, just 3 states in this case, along with some tabular data describing them. So unlike a traditional data set, which is mostly just a tabular data file, a spatial data set often links the tabular data set with a corresponding spatial data file that shows us how to, one, draw on a map, and two, also perform spatial analysis, knowing what things are near one another based on the coordinates that are used to describe those spatial areas. So a GIS data set is often combined a table describing what, and then some spatial data file describing where. And those things are just linked, one row in the spatial data table to one object in our spatial data file. Okay, so that's how we store spatial data. How do we map it? This is an older version of the desktop GIS software that I'll be doing a demo of in a little bit, ArcMap. And this is very much just like I think of it like an overhead projector, a set of transparencies that on the left you see a table of contents that we use to construct a map. Each and every one of those different rows, in this case, the GIS data layer I have circled is the state boundaries. You choose a way of drawing it or symbolizing it in cartography speak, how you want to order them, placing them on top of one another, and depending on the colors and the symbols, you draw more or less attention to certain things, and that's how you create a map. But that same construct of a geographic data layer with a table and the spatial component, you just add more and more of those together to create a map and choose to symbolize each of those layers in a particular way. Okay, so that's how we map. And then the analysis just kind of makes use of both those tabular attributes and the geographic information. So you can, in a GIS, run basic queries based on just the tabular data. So I'm not doing a spatial operation here. I'm just saying, hey, GIS, I want to run what's this, just a simple SQL query that says, show me all the states whose population in 2007 was greater than 5 million. If GIS is kind of fun because you can run the query and then your visual representation shows up in a map view. But you really don't need the spatial data to ask this query and get a list of the states. On the other hand, using the geography to ask a query, this is another really simple example, but hopefully it gets the point across. Here I'm asking the GIS in not SQL, but kind of in a spatial query language to say, I'd like you to identify all the states that share a border with these gray areas, which are the Canada and Mexico, another spatial data file. So my tabular data knows nothing about Canada and Mexico for the states file. It's just because they actually touch when they look at those geographic layers that allows me to query those. Okay. And similar, you can use spatial relationships in the tabular data to start performing more and more complicated analyses using GIS. So in this case, I just want to show you a different routine that kind of brings a couple of those things together. So my PhD is from the University of Kansas, Rock Chalk Jayhawk. We're pretty fond of basketball. In fact, it was invented by the guy who came to KU. It's kind of a big deal. Jessica also is very fond of another big basketball school and likes basketball as well. But let's just say for the case of this argument, we're looking at something that happens to most of us every March, kind of March Madness, and this fever sets in. So it's like an epidemiological model. So I'm running a spatial operation in GIS here that allows me to use the geography based on how the states are arranged to ask which states share border and are most likely to be influenced by Jayhawk's version of March Madness. Kind of fever, right? So GIS can allow you to select those states. In this case, there are 4: Colorado, Nebraska, Missouri, and Oklahoma. And I can run it again and say, okay, my theory is that you have second order spread. Your nearest neighbors and the nearest neighbors are the states that are going to be most likely impacted. And then I would like to run a model, let's say, that's based off of a distance decay function. So in GIS, I can say, okay, can you please give me the centroid of all of those states? It's just a really simple spatial distance calculation. And then I'd like you to generate the distance from the centroid of Kansas to all these neighboring states. And then maybe I'm going to dump that out, and I've got a model in R that I'd like to write and use that spatial information. But the GIS package allows you to visualize, do that nearest neighbor calculation, and then also do some distance calculations as well. Okay, so that's at a really high level, all the magic behind this, and then you can spend a lifetime learning how to actually perform the software, operations, make good maps, etc. But this is the gist of it. Okay, here are just a few slides of some of the fun stuff that if you were in a geography class, these would be entire weeks that you might spend on some of these topics. So we're just buzzing through them. But I think both Jessica and I, when we do these introductory workshops, like to at least tip our hat to all the other things that you might dive into in more detail if any of this piques your interest. Okay, so one thing that we spend a lot of time on are talking about spatial data structures, the choice of the right one to use for the right circumstance, and then all the cool operations that you can perform based on, in this case, really basic geometry that we learned way back when, but now applying them to really large data sets, spatial data sets. So the basic data structure, one of a couple, but the one that's most often thought of in GIS that people use frequently is a vector data construct, which is just based on this idea of points, lines, and polygons, right? Really simple. In this case, I've got an example of each kind of in a similar area and what a simple map would look like. So for points, a single latitude and longitude coordinate indicates the exact location of something on the Earth's surface, and each one of these cities will have a similar row in our data table that corresponds to it. Okay. A line is just a series of points that you say, start here, stop here, and any number of points in between from 2 up to infinity. And that line, the segment of the line, also has things corresponding to it. So roads, in this case, a line would be a particular highway segment that maybe is all of the same speed limit or road type. And then a polygon is simply a line that joins back in on itself and closes itself off so that you have a known inside and outside. In this case, census tracts, a boundary file that we will look at later on in this lab. And it's not a given that a particular type of thing on the Earth's surface should be represented by any one of these. It's kind of up to you to decide, right? A line in this case for a road is perfectly fine for a map of this scale that you're looking at this entire region. But if you were responsible for road maintenance and surface, kind of resurfacing of roads every year, you would probably not store those as lines. You'd probably store those as polygons so you'd know how much material to go out if you had to repair the roads. Same thing you're representing, it's just a different way of storing those. Key thing is in the GIS data structure, whichever one of these you choose, each individual point line or polygon will also have a row in your data table that has attribute information describing them. Okay. Believe this is Lincoln, Nebraska. If anybody's been to Lincoln, you can go ahead and raise your hand. I'll give you a gold star, a little trophy. So one of the other neat things you can do, given this simple geometric data structure, is you can start overlaying and asking questions of information, kind of like we did with that Jayhawks March Madness data spread. But there's a whole realm of different types of operations you can look at comparing those data structures to one another. So in this case, we've got a points data file that has crimes in a particular year and a polygon data structure that has block groups. I'm just showing two different examples of the points in the row corresponding to it, polygon, the row. We could intersect those two and start looking at, in this case, crime statistics and compare them to underlying characteristics of the block group and see if there are any correlations. Those sorts of intersection and overlay analyses are kind of at the heart of what's possible with spatial data once you put it into a geographic information system. Okay. And then there's a whole nother, some people spend their entire careers on this concept of cartography or how to draw a map correctly or incorrectly. The easier, and with the prevalence of software, over time it's become much more common to see really bad maps. I'm happy that people are making maps, but also it's really easy to make bad maps. And it's really easy to tell whatever story you want with a map. So it's really important as a map maker, you think about what your intended goal and audience is. And as a map consumer, you're kind of aware of what you're looking at. And you can always spend more time making your maps better, but definitely show them to other people before you get out there in the world. So we'll look at a few of these in our class today. I know, Jessica, yours as well, you kind of describe how you do some of these things in R. But just to give you an example, election long ago in the past, it's just always good to have look back on, depending on not only how you color code things, but just how you aggregate things, you tell completely different stories. So in this case, single red or blue at the state level looks very different than you disaggregate down to the county level. Or if you choose to not go with a single color, but a graduated color scheme, this is where we're not red or blue, we're shades of purple. That's kind of where this comes from. And then also to figure out who wins, you actually don't just look at the map as it appears in space. There are other types of representing space that weight the space according to what they mean. In this case, you win the presidential election based on electoral college votes, and each state has a different weight in that scheme. So here are two different ways of showing why, even if you looked at a map by area in red, blue, it might not look like you would win or lose. Here's what actually happens. And there's a whole wide suite of things that are coming online with much more cool interactive online mapping. And this one is great. This is not only showing single point in time, but multi-temporal data shifts in counties, as well as migration patterns, et cetera. So there's a lot of really neat stuff you can do with online mapping tools these days that were not possible in the past. Okay. Any questions before we skip into the last little section here? Okay, cool, thanks. So I just wanted to show a few things. Some of these are things that people have done after one or two CSD workshops. Other ones of these are things that have been, quarters, semesters, half years worth of work to pull off. I'm just going to breeze through them. This was in a master's thesis of an early CSD trainee that took a workshop that was looking at the relationship in Seattle of community or collective efficacy, the likelihood of people in a community to respond if something's not right, kind of qualitative measure, to murder rates. And this was just a map that she created after taking one of her intro GIS classes that she included in their thesis. So she shared it back with me, and I said, this is great. Really love when people are able to take what they're learning in the class and make something of it. This helped to visually represent some of the statistical model results that she came up with. I spent 5 or 6 years working with a lot of nurses, nurse practitioners, and nurse researchers that were looking at local health departments, how much money they have, who they served, and health outcomes that they represented. Part of my job in the research team was on our monthly meetings, I would bring different maps that would help showcase what data and what trends and patterns they were looking at spatially in the state of Washington. This happens to be an example of one of those maps for a brief I gave on teen birth rates and the change of those over time in Washington state. All done in ArcGIS, what I'm showing you here today. Working with some folks in the design department. They have an infographics course that a student came to me with the map shown on the left and said, these are all the parking tickets in Seattle, but my map sucks. Can you help make it better? So if you have over 500,000 points and you plot them all on a map, it's really hard to make sense of them. So there are different techniques for binning those into gridded quadrats, as we show in the middle, or doing a kind of a heat map where you smooth that data structure to find really the hot spots of parking tickets in Seattle. And the final map on the right was what they ended up using in their infographic display class. Have worked with a linguistics professor who printed off these paper maps, went to high schools around the state, gave them to people and said, circle on this map areas where people's English sounds different. And she came to me with a stack of 500 paper maps that she had scanned in and said, can you do something with these in GIS? So we digitized all of those maps, overlaid them on one another, and we're able to do some of the similar hotspot analysis to look at patterns and trends in the data and the responses that people gave. Really interesting that the responses had nothing to do with the people that were actually there. It was more people's perception of the people that were there, and linguistics was just a field that they were basically reproducing sociological studies in, which was really interesting. And then finally, taking environmental data, in this case, forest canopy cover in the Seattle area, creating metrics based on space, showing how much access people have to forest canopy, how near is any given spot to how much forest, and then comparing the types of populations that live in those areas. Those are the corresponding series of maps here from left to right. So all these types of analysis, all these types of different disciplines, spatial analysis can be helpful in those realms. Okay, thanks. I'm going to pause. Jessica, did you have anything that you wanted to add based on your experience and how anything differs?
No, I think there are some differences in how things work in R and what, when you might want to use ArcGIS versus R aside from personal preference, but I think it might make more sense for me to just address those as I encounter them.
That sounds great. Well, I agree with you. Do you have any high level, like if you had 10 seconds where you might draw those division lines and then I can compare them? Because I think that might be helpful before we dive into the software package so people might understand, okay, why is this set up the way it is?
So as Matt already mentioned, if your final goal is to do some sort of spatial statistical analysis and the package is in R, there might be a reason to just do your whole workflow in R, right? The other thing that I would say is everything that Matt's shown you, you can do in R, but some of the maps with a lot of layers are going to be much more easy to visualize better in ArcGIS than in R. You can do multiple layers in R, and we will talk about that, but sometimes coding it up yourself, even with the aid of packages, might take way more time than is worth it, depending upon what your goal is in visualizing the data and what you need from that.
Cool. I would buy all of that and add the reverse. It's also true when I was reading through Jessica's tutorial and thinking through this, I'm just blown away by how quickly you can do things that, yeah, are possible in ArcGIS, but would be so time consuming to pull off repetitive maps of the same type, just on different variables, et cetera. And absolutely, I've always found myself in positions late in a project that I'm like, okay, how the hell did I get here? Which buttons did I click? And how would I possibly redo this again? Of course, you could take good notes, go back, and ArcGIS has a Python underlying set of libraries that you could code against. But most people that are using the software, it's because they're prototyping a new idea and just thinking through something, but definitely not reproducible scientific research. You would want to write that down into code eventually before you finished a real research project.
I would also say, like in practice, like I've worked a lot with the city GIS specialist, but if your use of GIS systems is needing to look up a construction site in the city where you manage, or look up spatial data and query against it frequently just to grab an answer to fill out a form or to get an answer for an email for some other stakeholder, I think all of that is so much easier in ArcGIS than it would be in R.
Yeah, absolutely. I think a lot of those professionals as well use it for editing and maintaining the GIS data layers, because pulling up multiple things with satellite imagery or aerial photos and adjusting street center lines, et cetera, that's the bread and butter of what that GIS software package was designed for. Okay. Before we move over to our demos, do any of you all have any questions or comments or thoughts on whether it's pop or soda or Coke? Okay. Um, so I have got a demo of ESRI, Environmental Systems Research Institute is the company names. ArcGIS Pro is the most recent iteration of their desktop GIS software package that I'm going to run through. ArcGIS is a commercial software package, meaning it costs you money to use it. There are a variety of different ways that as students, staff, or faculty at the UW, you have access to download that software, put it on your own computer, or to make it easier so you don't have to go through that process to install a multiple gigabyte long process software and license it. Here at CSDE, we have a remote computing environment that allows people to log in from Windows or Mac computers to a Windows terminal server where we've already installed that software package. So, realizing that we opened this workshop up to a lot of people, including non-UW folks, this section that I'm going to go through now will be based on working in ArcGIS Pro and CSD's Windows terminal servers. Jessica, I believe your email this morning kind of sent out and indicated a note about that. So I'm going to go through the workshop. It's not terribly long, and just even kind of viewing along, asking questions, you probably get the gist of how this all works. But I did want to get a sign of how many of you all have a CSD computing account and are feeling brave and going to jump in and try and do this lab along with me. Thumbs up or a hand up. Okay, I've got one person. Alyssa, awesome. Okay.
It's asking me to log in. I don't know if I have credentials, but hopefully you'll cover that.
To ArcGIS Pro?
Yeah.
Totally cool. Okay, let's go ahead and get started and dive right in. That's helpful in knowing that there's a few of you. I'm going to say maybe closer to half, given that response rates are what they are. So feel free to pause, ask some questions. Some of this is just kind of mechanical stuff, so we'll try and get as far along as we can. If we end up getting kind of stuck, I'll just run through the last 5 minutes and showcase some of the things in how ArcGIS works, okay? So for those of you that are following along, I've posted this entire lab and walkthrough on our workshop website. So if you just go to our CSD website, csd.washington.edu, I'm going to go ahead and share a screen here really quick. And this will pertain to ArcGIS as well as Jessica's R portion of the workshop too. So I'm just going to our training workshops page, and then our spatial data analysis in R. If you go ahead and keep a tab open with this, it'll probably be helpful. So this has our Intro to GIS lab PDF, and then the R lab that we're going to do in a second is also right here. So if you'd like to go ahead and open up that PDF and kind of keep it alongside, that's just my operating instructions for what I'm going to be showing you here as well, okay? Okay, so first step is to open up a remote desktop in either Windows or Mac on your local PC. So I'm going to go ahead and do that. And then in the lab, you can see if you've got a CSD computing account, what I want you to do is either connect to CSD TS4, Terminal Server 4 or 5 if you're a student, or 1 or 2 if you're all others. So I'm going to connect to CSDE Terminal Server 2 and log in. As soon as I do that, I'll share my screen so we can just follow along together. And then Melissa, I think that will kind of catch us up to exactly where you're at. So looking at the handout here while my remote desktop is loading up. So for the very first time that you run ArcGIS Pro on any one of our terminal servers, you do have to specify your login information for ArcGIS Pro to work, and that's just simply your UWNet ID. You just have to tell ArcGIS Pro that you're part of the UW organization. So hopefully, Melissa, maybe you can tell me if you're already working on this while I'm just logging in here. When you pop up on the screen, you should see on ArcGIS Pro when you started up the ability to sign in using your ArcGIS organization's URL.
Yes, that was totally clear once I actually looked at your document, so I was able to log in.
Okay, perfect. I just wanted to make sure that that does work. I think I logged into a different terminal server than I did before. It should ask me, but just in case it doesn't, please refer to the handout. Okay, so I'm just going to open up ArcGIS Pro here. Okay, so hopefully, for those of you that are trying to log in, after you do so, you'll be presented with this screen here, and we're going to start an entire new kind of map project. So I'm at home, I'm going to say new project map. And we'll go ahead and name our project here, CSDE ArcGIS Lab. And then we'll tell it where to create our project, which will create a folder and a variety of files. So we want to make sure that we place this somewhere that we can get back to. So in our location here, I'm just going to click on our folder to browse for a location. And because you are on the CSD terminal servers, your home directory is the H drive. And I'm just going to recommend for ease of use, let's all go ahead and just navigate to this PC, our H drive here. And then let's just create a folder in this location. Say new folder. And we'll just call it CSDE GIS Workshop. Okay, I'll select that and say OK. So we're telling ArcMaps, hey, I want to fire up a new map, and it's going to set up our project file and a few other different things all inside of this folder, and that's what we'll work from going forward for the rest of the lab. Okay, so I'm just going to say OK. That will get this started. It will take a second because it's not only just saying, OK, I'm starting up the software package, it's actually creating some files and things on your computer. Okay. So here is hopefully what everyone who has started the software package should be seeing. I'm really quickly, while people may be catching up, just going to quickly open up a Windows File Explorer. I always like to see what's going on behind the scenes when I'm just clicking buttons. So it's not just a GUI, there's something that's happening. And I'm going to go to my CSDE GIS workshop. We told it we want to create this new project, so it creates a folder. Inside of that folder, it creates a variety of things that help get us started with the GIS project in ArcGIS Pro. This first folder, this GDB, is a geospatial database, which is a preferred way of storing spatial information, and that would be something I would cover in a different workshop, but creates a folder for that. logging, indexing, any messages get stored in here. So there is a reproducibility, although you have to come back here and look at the logs to figure out what you clicked on. Then we have our project file, as well as a toolbox where we might store any specific code or geospatial operations that we develop all get placed in there. We'll go grab some spatial data files in a second. We're going to put them in this exact same folder. Okay. So I'm just going back to ArcGIS Pro just to kind of look at the interface here. I have a 6th grader, and this new math stuff that they're talking about is real. It hurts my brain and it's hard. And why I'm telling you that is I have had to go back to ArcGIS Pro here in the last year and relearn it all over again because their previous software package that I had used for the past 15 years of my career is gone. This is just like the new math. It's a lot going on, a lot of icons and things to learn. Today, I'm just going to try and hopefully show you it's okay. We'll hold hands together, gently go into this. You can do a lot of cool stuff in here, but it's just like the first time maybe you've ever used Photoshop to do photo editing. It's really intense. There's a lot going on, but there's a steep learning curve for a reason because there's a lot of stuff that you can do in there. Okay, I'm just going to point out some of the highlights today. We won't get too crazy, but I just want you to feel okay if this is a little overwhelming. We'll just work through that together. Okay, so in the center is our kind of map pane. This is just like a standard, slippy map that you would use online. You can use your scroll wheel on your mouse to zoom in or out, reposition yourself in any particular area here. And as you zoom in, there'll be increasing levels of detail shown. It's pretty great. Over on the left side is our table of contents, which is where we have all of the layers like we looked at in the slides earlier that are drawn on our map. ArcGIS Pro just starts by default with these 2 layers that are actually coming from an online map server. These aren't locally on your computer. That's how they draw and refresh with more detail as they get further in. And there's actually 2 layers here. If you zoomed in far enough, you should see this. We've got the map layer and then this kind of hillshade overlay on top. If you'd like to, you can turn on and off layers by just clicking the boxes. So I can turn off the hillshade. Just kind of get a sense of how that layering works on the map and how you can turn one or all of them off, and then you're just left with a blank map pane. Okay. Along with the table of contents in the map, like any modern software package, you have tabs of grouped tools along the top. I'm just looking at one of them right now, our map tab, which allows all the functionality for us to interact with the map, how we navigate around it. You can zoom in and zoom out with fixed buttons. You can set spatial bookmarks. So if you have a few different views that you're going to create maps of, you can create bookmarks of those. If you accidentally screw up and zoom back out to the full extent, you can just go backwards and return back to the last view. Okay. And on. Each of these different tabs have a variety of different tools that you can use to add new data, perform spatial analysis, work with imagery files, air photos, satellite imagery, do advanced classification. There's a lot of stuff under the hood in ArcGIS. Okay. So this is great, but we want to actually look at some of our own data files. We want to bring our own information to the party. So I'm going to have you keep all this open, and then I just want you to start up a Google Chrome browser, which I just have the icon, and I assume most of the other terminal servers do at the bottom. If not, you can just search here for. And I'd like you to just quickly open up a Google Chrome browser, and we're just going to go back to the CSDE workshop page and download a few spatial data files, a few shape files, or the file format that Jessica put up here, and that these correspond to the same files that we're going to be using in her R lab here in just a few minutes. Okay, so I'm going to CSDE, back to our training workshops page, and to our spatial data analysis in R and ArcGIS. And then we have 3 different data files here: the census tract, census counts, and the open transit GIS files. I just want you to go ahead and download all 3 of those. So if you just click on those, I believe default behavior in Chrome is just, it's going to download them automatically to your downloads folder. So I'm just going to make sure I do that for all 3 of these here. and then come up here and see. Yep, it's like I actually downloaded one twice. That's okay. All right. So downloaded 3 zip files. I'm just gonna go back to a Windows File Explorer and pull out the spatial data from those and then show you how you interact with those in ArcGIS. Okay. So to do that, I'm just gonna open back up a Windows File Explorer. Here. Earlier I was in our GIS lab. I'm just gonna go to my downloads folder. I downloaded a second copy of this. I'm gonna delete that. So these are just compressed zip folders. I just want you to extract those into their own standalone folders. So each one of these you can just right click on and say extract all. I'm just going to create folders for all 3 of these here. This is our sound transit files. We'll be looking at some link light rail stations and lines later. Our census data table, and then extracting our census tract boundary files. Okay. So we have these 3 file folders here. Just select all of them. I'm going to copy those and I'm going to move them back over to our project where we want to work with them. That way we kind of have a single home for all of our data that we're working on. So I'm just going back to the H drive, our GIS workshop, and then our lab. And this is just a point of practice for decades of working in GIS. I always have created an original data files folder, which is where I will store the raw data. Hopefully this would have been where I would put the zip files, but the data that I'm going to start working with, and if I do modifications, it happens after here, but I always know in every project I've ever worked on, if I need to go back and find where was the raw data that I started with, it's always in this folder. So I created a new folder, original data files, and I'm going to paste these 3 folders of spatial data in there. Okay. So with that, I'm just going to show you how you can now look at a few of these data sets in ArcGIS. I'm trying to be aware of time, so I give you enough to do your portion. Jessica, feel free to holler at me if I start going over. Okay, so I'm just going back into ArcGIS, and I would like everyone to add over on the right-hand side, if they don't see it, what's called the Arc catalog, which is kind of like the file explorer that works inside of ArcGIS. If you don't see this over here on the right, it's not a problem. We can go ahead and add that pretty easily. I just want you to go up to the View tab here on the top. And where it says Windows, these are all kinds of things that you can show along your display here. This first one on the top is for the catalog. So that will add this over here to the right. Because we placed all the data files into our working folder, if I just click over here on the right folder where our project is located at, this will now show us in the same pane that entire structure we were just looking at externally in Windows File Explorer. Okay, because I always name this the same, original data files, I know that's going to be there, and we're going to start by adding our census tract boundary files to our project. So I'm going to expand that. There's a few different files in here. The .shp is the vector data file format. Jessica, I know your lab has some more details about those that started with Esri and are now pretty commonplace. We can just take, drag, drop that onto our map. So I just took this shape file, draw it on here, drag it over here. That adds that to our visual display, and that also adds that to our table of contents. Just like before, this is just a layer that's drawn on the top. This is the top of our stack, so if I turn that off, it disappears. If I turn that on, it reappears. Okay, same sort of thing before. We can navigate, move around the map, zoom in or out. Now that we have a polygon track file, we can do one other thing, which is interact with that layer. This is maybe another difference between R and ArcGIS. If I'm just exploring, I might want to say, okay, what do I have for this particular tract? I can click on it and bring up the tabular information that I have stored in my data table associated with that one feature. This is just one row. So you can see a lot of this is just administrative information about the census tract. its number, where it was located at, etc. Okay. So in our map, we have our visual representation. Behind the scenes, we have a table of information that's stored that also is part of the GIS package of a shapefile. I'm right-clicking on our tracks and saying attribute table, and that's a way to open up the tabular information that corresponds to the map data. These two together are what make up a vector shapefile in GIS. So if I select any row here, it's a row of information, I've selected a feature. You can see on the map, maybe you can't see, I'll right-click here and say flash. That will show us. That is one row. It's just the reverse of what I did a second ago, and you can see all of the variables associated with it. Example I gave with some of the queries in ArcGIS earlier, which were just performing a selection based on some attributes in the data. So under our set of selection options, our first one is select by attribute. So I'm just going to click on that. And I just want to select from our data set all of those census tracts that are in King County only, Washington. So from our tract data file, I want to create a new selection, and then you just essentially point and click a SQL query where our name LSAD county is equal to King County. Apply. It's going to say OK. So in our data set, we now know 494 of our 1792 tracts in all of Washington are in King County. And you can see those displayed on the map. Selections are often done when you want to run a geospatial operation on a subset of things. First, you can select by attribute, and then any tool you run from there on out will go ahead and only run on those. Okay. I'm going to go ahead and clear the selection here and say, okay, that's what I want. That's all I want for my map are just those counties in King County, or those tracts in King County. So the last thing I'm going to do, I'm realizing I'm a little short on time, so I'm just going to wrap this piece up so I can hand this off to Jessica. But in our tracks over here on the left, if we would like to get kind of behind the scenes and configure a lot more of the options that we have for this particular layer, you can right-click on it and go to Properties. Yeah. Oh, sorry, you just double-click on it. Again, new software package, still learning. And in this case, instead of a selection, which is a temporary operation, I actually want to set up a, it's called a definition query that basically says I have my larger data set on disk. I only want to do a view of it that's just a particular subset for mapping. So I'm going to go back and do the same thing here. Name LSAT is equal to King County. Apply. And now when I say OK, our map is simply just showing King County, what we're going to be working on. Kind of hand this off to Jessica here in just a minute. The last thing I want to show you is just how mapping and symbology works in ArcGIS, and I think this will be a good spot to pause on my demo and hand over to you, Jessica. It's kind of more the interactive kind of cartographic design piece of ArcGIS, and then the same thing can be done in R, just more written in code. So in this case, I'm going to right-click on this particular layer and go to the symbology, which is basically how we choose to draw any of the features on the map. This is a pretty simple example because we don't have a lot of data that we would really want to be mapping against. I'm just going to come over here and say we do have some area of land and area of water. It's a rough starting spot, but that will work. So right now, my symbology type is a single symbol. I can click on that symbol and choose a predefined boundary file type symbology, or you can go in excruciating detail and make the most awful color choice for symbology boundary file that you want to. You can do whatever you want in here, all that's possible. So along with just a single symbol for all your layers, where the real mapping fun gets started is when you use some of your attributes to actually define how you want to color code things. So in this case, one option is I want to have a single color for any unique value I have in a field. Kind of a poor example, but let's just go ahead and say this is our census tract name. So based on any census tract we now have a super huge legend of 474 unique colors that were just drawn. Again, not a great map, but just want to show you the point. Last one, where I think, Jessica, you have a lot of examples of these, are using graduated colors, or what would be called a thematic choropleth map, to pick another one of our fields to create categories, bins, or ranges, and then a color associated with them. So in this case, I'm just going to select our area of water, choose maybe a more appropriate color scheme for water, and then zoom in here a little bit. So now, based on the area of water, in this case, mostly rivers up in the mountains or around Seattle, census tracts actually extend out if you happen to be on a lake into the center line of the lake. So many of the census tracts you see in blue here along Lake Washington or out on Vashon. So the intersection of the tabular data, the spatial data, and the symbology allow you to start making some really rudimentary maps here. Okay. Because I'm a talker, I've run out of time, but you have the workshop if you want to kind of go through some of the remaining components there. But I'm going to pause what I'm doing and hand stuff over to Jessica. Before I do so, do any of you have any quick questions related to ArcGIS and what we were just looking at, so I can make sure to address those before we move forward? Awesome. Okay. Thanks, Jessica. Sorry I took up 5 minutes of your time. Hopefully you won't hold it against me.
No, I was happy for you to keep going as well. Let me make sure I have the ability to share my screen. Can you all see this? Great. Okay, so we are going to use only one of the files that you downloaded from with Matt, and that's going to be the sound transit data. We're going to go over, we're going to start by going over the tidy census package, which will actually give us census data with geographic information from the get-go. I think for those of you who are interested, I'm happy to send the RMD around. But I think the HTML file is easier for you to use as a resource now in the future. It sort of reads as a narrative. First, we're going to make use of these different libraries, and we're going to focus on these first three in terms of spatial data. Tidy Census is a package that interfaces with the Census API and also provides spatial information, and it makes use of the Tigris spatial package, which is sort of the census's geographic information system. And then the SF package is, I would say, the primary workhorse of GIS work in R, but it is not the only one. And then here are some extra plotting packages we're going to use. I just want to call out some important resources here. So SF is downstream of also maybe Matt, if there are questions that are coming through the chat that are pertinent, will you let me know, and then I won't pause when I see a chat come in?
You betcha. Yeah. Happy to do that. The only one was saying your RMD suggestion would be great if you could pass that around, but I'll holler if anything else comes up.
Okay, great. So the SP package was the original R package that did any sort of spatial data wrangling, data analysis, and it was developed by Roger Bivand, and it came along with this R textbook, Applied Spatial Data Analysis in R, and this was sort of the Bible for spatial statistics in particular. Remember, I sort of mentioned that that's one benefit to using R, but a lot of the stuff that Matt is talking about and the like original purposes for developing, say, ArcGIS and other software were not to do spatial statistics. It was to make sense of spatial data in general, which does not have to involve statistical analysis. But for us to do statistical analysis, there was a need to merge a lot of spatial GIS functions with the R package. So when SP was deprecated and retired about 2 years ago, Bivend and colleagues rewrote a book that's now available as an ebook that deals with the SF package. So a lot of my materials will be based off this. There's a nice cheat sheet there. There's another really good ebook called Geocomputation in R by Robin Lovelace and colleagues that covers the SF package as well as 3 other packages, the Terra package, which a lot of people will use, the SP data package, and the SP data large package. There's also a raster package that's helpful for raster images, or what I might think of as a statistician, continuous space data. So if we have, say, air pollution data that we know that the reading is tied to the single GPS location of the monitor, we might want to take all of continuous space, chop it up into a fine grid, and say this pixel where the monitor is the one with the data. There's a couple packages that I'm not going to talk about today, including the raster package anymore. TMap, leaflet, and map tiles. And if you really want to make good maps that geographers would be proud of, I think pulling these resources into your visualization process is important. TMap is a little bit more high level and will do a lot of work for you to make some nice maps, but is maybe a little bit more difficult to customize. Leaflet and map tiles in particular, Leaflet is designed to help you make interactive map products. And then map tiles is really handy. Leaflet as well can incorporate things like Google Maps data or that underlying layer that you were seeing in ArcGIS as soon as you opened the software. Map tiles is a way of getting stagnant Google Maps data. So if you want to make a good stagnant map and street level or city level or neighborhood names, something that's coming from Google Maps is of interest, contextual information. It's a really great resource, but it's a lot of trial and error to sort of get the right one in a stagnant, you have to pick the zoom of Google Maps and as it corresponds with your data. So we're not going to go over that in the next hour, but I want you to know that they exist. There's also packages such as QGIS process that interface with QGIS, which is sort of the open source version, GUI version of ArcGIS. I don't know if there's one for ArcGIS, but I would be surprised if there wasn't. And then there also, as Matt mentioned, there are a whole suite of Python packages. I'm sure what I have here is a small subset of what actually exists that allow you to do similar things that we're going to talk about here, just in a Python script environment. Okay. So as Matt talked about, there are kind of 3, I would say, well, 4 canonical types of spatial objects. There's point data, which are non-contiguous spatial points. There's lines, which is essentially a collection of infinite spatial points that all are next to one another. And then we have polygons, as he mentioned, and in practice, these look like things like nations, states, counties. As Matt made the point of earlier, I list streets here as lines, but really the way you want to classify spatial data is wholly dependent upon what you are trying to do with it. And then pixel data, which we're not going to spend a lot of time on, but this is where imagery data or remote sensing data, or as I said, if you have continuous space, numeric information, maybe you want to discretize space at a fine scale to attach that numeric information to it. All of these are handled very well by SF. I just want to make a point, if you're ever reading legacy code, that SP had separate object types for each of these things, and you had to be very specific about whether it was spatial points or spatial points data frame with attributes attached. But SF kind of treats them all very similarly. So we're going to start with polygons and the tidy census package. This is just really handy for pulling any spatial data if you're going to use it in R and it comes from the US Census. It doesn't interact with all census APIs, but it does interact with the census, decennial census and the ACS APIs, amongst some other things. You can get data from this without using, without spatial information, but you can also get spatial data with spatial features attached. So I'm going to turn now to R and kind of run some code here. First, I'm going to set my library. Wherever you put your data files, those folders we downloaded, is a fine place for you to set your library. I would use it do this using my setwd function, but if you're more comfortable with point and click, or you don't quite remember or know the file path of where you put your stuff, you can go over to files and navigate, and if you find the place you want there, the folder, you go inside of it and say set as working directory. Also in the session tab, this might look slightly different if you're on Windows, but there will be a session drop down. There is a choose directory, and you can go through your GUI and find the folder. I just want to note that my code is written where this is my working directory and the data is stored in this folder. So I'll give you a heads up when we get to the lines where we're loading the data and show you how you might want to modify your code if you set your working directory to, which I recommend, a folder that looks like this on the inside. Okay. So I've set my directory. You'll know if you've set your directory to the right place by either going to this files pane and now clicking go to working directory, and you should see the file or the folder you wanted to go to, or you should see the working directory path here in your console. Okay, I think there's someone's mic is on. If we could mute our mics, that'd be helpful. So I'm going to load all of my libraries here. If you don't have these packages installed, you can uncomment this line and keep adding any of these package names with comma separating them, install the packages first, and then run each of these lines separately. Okay, so this part is kind of specific to how I like to work with the census API and share code publicly. You don't need to do it this way, but if you did fill out the request to get your census API key, maybe I'm going to shorten this so you can't see my whole key, then go to the email where you got that key, come into your R console, and type the following code, my key, use the left assignment arrow, start some quotes, and paste that alphanumeric string in between your quotes, okay? So let me know if you have troubles with this, but once you've done that and you have an object in your environment called my key, then you'll run this function that's just going to specify your API key. And then this is also a tidy census option that will just cache shapefiles so we don't have to load them every time we use them. So there's a lot of information in here about how to work with the tidy census package. I'm going to try to kind of speed through this quickly because it's not pertinent to GIS, but I want to lay out why we're doing it and what to expect if you ever do this on your own. So there are functions in the tidy census package that will list out all of the variables in a census data source. So here's an example of all of the variables from the 2021 ACS 1-year sample that have what they call a concept of sex by age. You'll see that all of these variables have the same name prefix, and then the suffix is different. And then in the label, you can see this kind of nesting set of strata defined by the concept. So the first row is the total. This is going to be the estimate of the total population of all sexes and all ages in whatever area we specify in that year. Then we have a total for just male. And then we have the male breakdown by sex. If you kept going and looked at this, we would eventually get to estimate total female and then all of the ages under the female branch. So these are a little annoying to work with. So some of the code that I have below here is just string manipulation to clean those up real easily. The other thing that I also include in here, which is just handy if you've never done this before, is my suggestions for how you find variables you want. We're going to work with the decennial census today, which only has 6 concepts. And we're going to work with the race concepts. That's just going to be population breakdowns by race. But at the ACS level, there are thousands of concepts. And so this section is just some advice for how one might efficiently search for the variables they need. Now, the main functions that we're going to focus on from Tidy Census from now on are the get functions. This is how you get data out of Tidy Census. And we're going to use the get decennial function in particular to get 2020 decennial census data. The geography that we want to specify is the census tract. You can specify state, county, tract, block group, or block, depending upon the type of data that you're requesting. There's an option to specify a single variable, or we can specify a table. A table is the same thing as a concept in the variable table that we were just looking at. So what I'm pulling here when I say table equals P1, I want every tract level variable, which is a population count from the 2020 census, broken down by all of the possible race responses that are reported publicly. And we'll see what that means more in a minute. I will tell Tidy Census what state I want information from, what county, the year I want the data from, and then in decennial, this is called the summary file. So if you're pulling from information from the 2010 census, there's a different file. You can read documentation to figure out what that is. And then most importantly for this workshop, we want to specify the geometry argument as true, okay? Also, when I share my screen, I can't see your faces. So if you do have questions, feel free to just unmute and ask them. So to follow along in code, I am going to use this load variables function to store a data set called decennial variables, or the shorthand form of that. And just to show you what this looks like, we have a concept called occupancy status. These don't have the word estimate in front of them like the one I just showed you, because this is not an estimate, it's the population count. So we have the H1 table is the occupancy status, and this is going to report housing units, totals, and then broken down by occupied or vacant. The P1 table that we're going to pull is the race concept, and it's going to have the total respondents, or the total count by geography, the total population of one race, the total population of one race who responded white alone. And then this gets broken down much further, total population of 2 or more races. And just to give you an example of how detailed this could get, it gives you all of the combinations of 2 races someone reported that could be published publicly and meet differential privacy restrictions. And this goes all the way down to 6 or more races, but we're not going to deal with all of that. So let me go through my examples. Okay, so here's where we're going to pull the data. I'm going to run this get decennial function, and I'm going to store the output of that in an object called KingCoPop. All right. So if you've specified your census API key, you should see the exact same messages in your R, and then you should now have an object called King County Pop. And if we look at this by just clicking on it in the viewer, we have just a few columns here. These are the things that previously Matt referred to as attributes, these first 4 columns. We have the GeoID. This is the unique numeric identifier of the census tract. We have the string name of the census tract nested within county and state. We have the variable name for that tract, and then the value from the 2020 census. And now we have a separate column called geometry, and this is what makes this an SF object, or a simple features object. And you can see that because tracts are polygons, it's telling us that this is a multi-polygon object. And you can see the beginning of a bunch of GPS lat long points that are going to be used to draw that polygon. Okay. So, and just so you can see how this looks in some other ways, you can see that this SFC multi-polygon would be spit out as a class. This is also, there's a lot of other attribute information related to the geometry that's stored if you look at this in a different way. So, here for this table, we have 71 unique population counts of population by race. No one is ever going to remember the alphanumeric variable that you want to use, right? So, one second. A note on GeoIDs, if you aren't familiar with census geographies, this can be helpful. It just tells you what digits of a GeoID represent what geography. But we can use this output of load variables that we saved earlier, join it back on this output by the variable, and get this label information out that we saw before that can give us some reasonable columns or attributes in our data that make it easy for us to understand what each value means in each row. So all of this code that I'm going to go through next, this is the kind of thing that I said I'm not going to spend a lot of time with. Every time you pull from Tidy Census, if it's a different data set, you're probably going to need to do this slightly differently. But this is a paradigm that you can use. So you'll save the output of load variables. You're going to left join that output onto the output of your get function. And then you're going to have to do a lot of string cleanup. At the end of the day, we're going to end up with a product you'll see that has some easier to use variables. So I'm just going to go down to the code. Here, I'm going to left join that variables data set on and just reassign the output of this to something with the same name. This is probably not the best coding practices, but it's what we're going to do. And now if we look at the this object, you can see I have this label column in here, but it still has all those really annoying exclamation points and colons, and we hate that. So all of this is just my way of getting rid of this. If we have time at the end and you have questions, we can walk through this, but I don't want to spend a ton of time on this today. To see what the output looks like, I have cleaned up the label and gotten rid of different things, but really I don't want to use that label column anymore. What I've actually done is create 3 columns. Remember, these were these kind of really complicated nesting labels where we could get all of the respondents of people who said they had 1 race, and then people who said they had 2 races, and then we could get subgroups of that, and then 3 races and subgroups of that, and so on and so forth. For this exercise, I thought we would focus on people who respond with 1 race alone and record their race, and people who respond with 2 or more races and just consider that our full universe, okay? So this required the creation of these 3 columns. This category, the one that is total, this is the total population. If the category is population of 1 race, then the race alone column will have a race in it. If the, let's maybe look a little bit further here, for population of 2 or more races, if that's the category, and race alone is total, then this would be all of the people who report 2 or more races. And then you can see on, I could have done this further and further, but we see these breakdowns of the other categories, but we're not really going to use those today. Any questions about what we've done here in the data product we've created before we visualize it and start to do anything spatial? Okay, great. All right, so unlike ArcGIS, we've loaded spatial data. We have some in our R environment, but we can't interact with it in the same ways that Matt showed. We can't just zoom in and out and see what we want. So we have to be kind of intentional about how we visualize it, what we visualize, et cetera. Like I said earlier, there's plenty of different packages that can improve your visualization of spatial data, but we're going to focus just on using ggplot2. And if you're familiar with ggplot, you know that any type of data visualization involves a ggplot call and a geom something call. For spatial data, regardless of whether it's points, lines, polygons, etc., you will always use geom SF as your function. So if what we want to do now is plot King County tracts with total population, perhaps the simplest thing I could do is filter. Remember, this object that I've created has 71 rows per tract. I just want to focus on total population. So I'm going to filter down to where the race category is total. And then the most basic plot I can make of population with no bells and whistles, totally default, is to pass that filtered data set into ggplot and slap on a geom SF layer where I let the fill be determined by the value column, right? And that is the total population of that census tract. So if I run this, or if we return to the HTML, we see this nice figure. We have grid lines in the background. They default to the gray with the white grid lines, just like regular ggplot. We have lat long, that could be helpful. Some negative things here, we don't have compass rose, we don't have an inlaid legend, we don't have anything that tells you about how, about scale, right? All things that are important for a proper map. But I am often using GIS, and this may not be true for you, so you may have to do different things, but I am often using GIS to display information across space that really has less to do with the geography and more to do with, say, the political boundary or the cultural boundary or whatever. So while all of those things are important, if what I want to get across is what census tracts have the highest population, I probably don't really need to display latitude and longitude to do that. I don't even actually really need to tell my viewers which direction is north. Matt and I might squabble about that, but just remember that what we're going to go through today is the bare minimum, and you should be thinking about all of these things in terms of the application that you do. All right, some major problems with this plot. What does value mean? Hate that. The legend doesn't have a name. I don't really even like continuous scales for things like population, but we can talk about that in a second. And I really, really hate the default that dark colors are 0. So that's another thing we can change. Any other issues people have with this plot?
I don't think the lines are clear enough personally.
Great. Anyone else? Another thing that comes up a lot when you're looking at pictures of King County is where is the water? Again, that might not actually matter if what I'm trying to do is just display population, but for people who are familiar with the area, making sure that water is visible can really help orient a reader to location on a map. Okay. So we're going to go through now some things that can help us clean up or make a tidier plot. I'm still going to filter down to the total population. Here, I'm going to adjust the size argument. This is going to adjust the width of the boundaries. This becomes a bigger issue when you have smaller polygons, like when you have urban census tracts. So I usually like to make those really small. If I wanted to adjust the color of those, as we will see in a minute, I can adjust using the color argument. The important thing for those of you who aren't familiar with ggplot is that any aesthetic argument or manipulation that comes outside of the aesthetic function is going to be like a hard code. It's just something you want to be true for the whole plot. anything that is going to be colored or drawn as a function of some variable in your data, whether that's a continuous variable like population, or whether that's a categorical variable like whether your county voted for Obama or not in 2008. So here's a function. We're going to go through a couple of these, but these are the kind of thing like just go Google scale fill chloropleth map in R, and you'll probably find a million other functions that I'm not even familiar with that allow you to customize colors and whatnot. Scale fill is a suite of functions that allow you to manually change the way your aesthetic, so a fill argument that's within the AES call. So here I'm going to change the direction to -1, and that's going to get rid of that issue where dark colors are for small values and light colors are for large values. I can also change the name of my legend to be something more informative here without having to manipulate the variable names of my underlying data. I can add a title, and I often like to make my maps with theme void when what I'm doing is displaying discrete data or summary data at discrete spatial levels. And that will get rid of some of the extra ink in the background that might be distracting to certain individuals. So Barbara, does
That looks great.
All right. Anyone else have issues or thoughts comparing this to the last one? Matt, do you have anything to add about making these decisions?
North is always up. So if you stick to that, you don't need a north arrow. No, this is great. And I appreciate your some of the fixes so far. The choice of colors there's a lot going on there for sure. And I really appreciate that you're going from one to another. Generally speaking, for single variables, we would choose a single color going from light to dark, but this is another great one to really help make things pop. So doing great.
Great. So, and this is just a note about color choice. This scale in particular, or palette, is intended to be good for color blindness. I want to caution everyone when you to not ever make blanket decisions about that. There are certain things that are more common in terms of color blindness, and these are good rules of thumbs. But always, in whatever capacity you have, work with your team, work with stakeholders if you have, and if there is anyone with you that has trouble interpreting any figure you make, adjust to fit that. There's no one size fits all solution. I generally agree with Matt that I would prefer 0 to look something more like white and to follow a continuous gradient in one color. Okay, so what if we want to plot multiple variables on the same map? There is a nice function called facet wrap. If you're used to ggplot, you've probably used this for other types of plots. And this will automatically make a multi-panel plot where every panel is a unique value of the faceting variable. And it'll ensure that you have one consistent legend for all of these maps. Then we'll go through an example of how you might create these maps by hand. If you want to paste them together, this example that I'm giving you is like not really, why wouldn't you just use facet wrap? But I think sometimes, right, we're not actually plotting the same variable. Sometimes you might want to see population and you might want to see housing and those next to each other. And this is a solution for that. Okay, so using facet wrap, I'm gonna filter down our big data set that has all 71 race variables for all census tracts in King County to a pretty annoyingly long query of my created variables that will get us down to what I said before. This will be a complete count of King County's population broken down by all of those who responded to the race question in the census with one single race broken down by that response, and then everyone who responded to or more class together. I'm going to simplify these levels to make prettier plots into these sort of shortened forms. So this will be 2 or more races. This is Black or African American, American Indian and Alaska Native, Native Hawaiian or Pacific Islander, Islander, and then some other race alone. So that means they only responded with a single race, but it was not clearly one of these three, along with white and Asian that are fixed up by this line. And then I pipe it into ggplot. This geom_sf call looks just like it did before. I'm still using the same color gradient. Maybe we don't love that, but that can be easily changed. And then all I'm doing to the code above, besides this kind of pre-work I did to make my legend a little prettier and easier to manage, is add this one line, facet wrap _race, which is this new variable I created that has these unique values. And now if I run this, you should get the plot in the HTML. Again, I don't love this plot really at all. For the reason Matt said, this is a lot of ink to show a lot of zeros. I kind of abide by the data visualization rule and the statistical and philosophical rule of the principle of parsimony. But the way that translates to data visualization is that there really should, any ink on the page needs to be useful. We don't need a color to represent nothing. So that would be one complaint I have here. The other thing that I don't really love is that these automatic breakdowns are basically saying we have close to 0 people of many of these race categories in basically all tracks. And then we really get to see the variability in the white population, which is just variations on a lot, right? This makes the color gradient evenly divided, which might be nice for interpretation. However, I don't really think it's useful. I don't actually need to make this map to know that Seattle or King County is mostly white, right? I want to learn something else from all of this data. Here I am going to show you how to make a plot like this by hand. And then when we do this, we will make our own categories for a discrete set of legends. So I'm going to take that big data set we had, I'm going to filter it and clean up the race variable as I did before. And then I'm going to use pivot whiter. If you're not familiar with this, basically what this is going to do is I'm going to end up with a data set now that has the number of rows of census tracts, so 1 row per census tract, and instead of 1 row per census tract in every race response, I've made all of those values columns. Okay, so that race variable, now each level of that is a column name and there's a value in that. Okay. So when I want to make choropleth maps, and this is very much a style thing. This is not the way to do it. I think I would love to be in a room full of people who would argue about this for a couple hours and, read a bunch of papers. But there's a lot of things you're trying to balance. And so I think some of these decisions really should be informed by the research question you're asking and the type of data you want to display or the point you want to make. As a statistician, one thing that I really want, and also I would say this is kind of in my demographer hat, is I really want the variability across space to be seen. So if that means, as in this case, we have a lot of tracts that have large populations of white people, but then we have a lot of tracts that have smaller populations of other races, I don't want to think about variability just between the minimum and the maximum number that I'm trying to plot on my maps. I want to highlight differences kind of at all stages of the distribution. If things are basically the same between the 25th percentile and the 75th percentile, then I'm going to chop up the ends into finer categories so that I can really see the range of diversity in my polygons for whatever variable I'm looking at. Other people may have other ideas. A common thing would be to choose quintiles or quartiles or deciles. So this isn't reproducible. This is kind of the one, I would say, artistry thing I do when I'm analyzing spatial data. But here I'm taking that data set and I'm just looking at the range. So I know that at the low end, I have tracks with 0 populations for some race categories. At the highest end, I have 6,272 people, assuming that's probably for the white respondents. Here, I'm going to do the same thing, but I'm going to get the deciles every 10th percentile. And this is going to really help me see, okay, but what's going on in between those 2 points? And here I see that only 10% of the data lies between 2,000 and 6,200. But when I look back at this legend, I'm using, what is that? 67% of the color gradient to represent that variability. That doesn't seem like a very fair representation to me of the variability of population sizes by race category that we see in our data, right? So this is not necessarily the breakdown that you have to use. This is a breakdown I chose based on wanting to kind of summarize different pieces of the distribution while also sticking my categories or my breakpoints to round, easy to digest, quick to read numbers, okay? So in each of these cases, I'm taking that King County Pop wide data set that I created. I'm applying this really handy Tigris function called erase water, and that's going to get rid of the water tracks. And then here I want this is just going to be a map of the population of white individuals. So the column name that I want the fill variable to be determined by is called white now. And then I'm using the same scale or palette that we don't really love. I'm turning it light to dark. I'm changing the name so that it's pretty. I'm adding my custom breaks and my custom limits. I'm changing my title and I'm running this. And since I'm assigning it to an object, it's not going to spit out the plot. These messages are coming from our erase water. And if we just look at this real quick. Oh. You can see now that the water's been cut out. I can see where Mercer Island is. I can see where Lake Sammamish is. But I'm also picking up a ton of little ponds and stuff over here that maybe aren't so important. So there is an argument that you can change called area threshold. It's a number between 0 and 1 in the erase water function. And this will kind of change the size. It's really the proportion of bodies of water. Like if I say threshold is 0.99, I'm only going to cut out the largest by area top percent of water. So here I'm going to make one for the Asian category. I'm only changing the fill argument in my title. And I'm going to make one more argument for the 2 or more race responses here. And then I'm going to use the grid arrange function. And this is how you can arrange on your own multiple ggplot objects into some sort of grid. This can get really flexible. You can actually have things that are different sizes. This is just going to give us a 2x2 grid with 3 plots in it. And so if I run that, I think this gets spit down here. You can see now that these 2 plots, once we change that area threshold on the erase water, is not getting rid of, or is kind of mapping over or subsuming into the land, if you will, a lot of these smaller bodies of water, but we're still getting those important features that might help someone orient on a map. Things I hate about this, which gets into my previous comment that I actually don't like using continuous scales for chloropleth maps, is the legend, the way we've broken it up, it is showing variability at these scales that we wanted, but this legend doesn't look very nice, right? It's really hard to read. So we can fix that by using a discrete legend. Before we do that, though, I just want to check and see if anyone has any questions.
Can I ask one? This is awesome. Can I ask one really quick? So another thought that I had that is, could you also be showing this by proportion of race that would then normalize? So if you divided by the count by the total, then it would be the same scale. It would still highlight the highs and the lows and be, is that something that would be fairly easy just to whip up as well? Just
Oh,
divide.
absolutely.
Okay, cool.
And
Not on the lab, but
one way that would make that very easy is when we make this, sorry, up here, this wide object, if we kept the total, right, that would be another column. So you could just divide each of these columns by the total or by the sum of each column. It would be very easy in R. And I think this is one of the benefits of R that I don't know exactly how these things work in ArcGIS, but sort of any function of your data that you can do with any other data frame that's not spatial in R, you can do with a spatial data frame.
very cool. And thanks for the example. Yeah, that might be 15 or 20 minutes of going back and reclicking all over again versus just changing a line and rerunning. Great, thank you.
Awesome. Okay, so we're gonna make discrete plots, and I'm gonna use our color brewer. There's a million other palettes. This is one of those things I mentioned where there's a million options. Google, find the things you like to do, but I like the R color brewer functions because they have nice ggplot functions that interplay with their palettes. And I just want to show you real quick. You don't actually have to load this package to use this, but if you do, you can display their built-in palettes. And so you can see here at the top, we have these sort of light to dark gradients. Some of them are this multiple color, which might help with certain types of color blindness. A lot of them are single colors where, which is also nice for color blindness. Like a lot of times saturation is hard to distinguish regardless of what color it is. So having increasing saturation of purples or of blues or greens can be good. There's these categorical palettes that are designed to just have unique colors that are easy to distinguish between one another if you want to display categorical data. And then I think one of the best things is that there's a bunch of built-in divergent palettes where you have some sort of scale with a sort of center or a neutral, maybe 0, and then you have two different palettes getting increasingly darker as you move away from 0 or your center in either direction. So that is how I am choosing the color palettes in this next set of code. Here I am just making a new object. We probably should have done this a long time ago, where I'm removing the water so that we don't have to keep doing that every time we make a plot. And then I'm just copying and pasting some of this cleanup code from before. So this object now that we've made has one row for each tract and level of the race category. Okay. So then again, very simple, ggplot, geom_sf. I'm going to fill with the value column. Here I'm going to change the colors of my boundaries. I'm going to make them really small because in the small urban tracts, it's hard to see the colors when the lines are really big. And here I'm using another scale fill function. This is scale fill for Minter. So the R color brewer package is clearly written by someone who likes to homebrew, and all of the accompanying functions have brewing names. So fermenter is one that allows you to pass a continuous variable and a set of breaks, and which is different from what we did up here, which was using that Viridis palette. And it's actually going to make a set of colors, distinct colors for the set of buckets that you define by these breaks. And so I'm going to use the yellow, green, blue palette from our color brewer. I have passed 10 breaks, which will give me 9 colors. And then here I'm still going to facet wrap, so I'm not going to do it by hand. And then we've seen the rest of this before. And so here, I think we see what I would argue is a bit more informative plot with a nicer legend. It's still very hard as we make these small for the lines in the urban tracks to not kind of outweigh the information. But this is a case where I would say there's really no solution. The solution would actually be showing another set of maps that zoom in on Seattle or Seattle and Bellevue, and kind of cut off these rural tracks so that we could have the big view, and then we can zoom in and see more detail. So if we want to do this by hand, we're going to do something similar to what we did before, but we're going to use the scale fill fermenter instead of the scale viridis. And I'm going to make these separate ggplot objects for these 3 racial categories. There's one argument I'm going to add that we haven't seen yet, which is called show.legend. And so by default, this is true, but if you want to do a multi-panel plot where you actually do have the same legend and you don't want the legend to appear on every plot, you can do this. So I'm going to make the first plot without the legend, the second plot with the legend, the third plot without it, and now I can use that grid arrange function, and we can look at 2 subsets here of the race alone categories, or single race alone, in a bit more zoomed in fashion. Okay. Any questions before we move into the next section?
This is just your 5-minute warning, Jessica. 5-minute warning.
Oh no. Okay, I was thinking we had till 4. I'm going to speed up. Okay, so what we've done is plot with data that we pulled in from Tidy Census, but what we really want to do is combine spatial data. So you'll use the read SF function to load your data, and we're going to load the link stations wherever your working directory is. So go to your working directory. The DSN argument should be the folder that contains your data. So for me, this is the data folder and the ST public data. For you, it might just be deleting these and saying ST public data. And then if you open this folder, you'll notice that there are a lot of different files. And I'm just going to load the stations and the lines. That's what the layer argument is for. Okay, so DSN is like directory. And if we load that, we can see I have this new spatial data set that has the stations. And then I can see over here, it's a point data set. If I load the lines themselves, I can see that this is a multi-line string. So when we want to combine 2 different data sets, we have to make sure that they have the same coordinate reference system, or are drawn on the globe in the same way, if you will. The stcrs function is how you get R to print out what some object's CRS is. The main thing here is that we want to make sure all of our objects are on the same CRS. So I'm going to use the st transform function to convert the stations and the lines to the census data geography. And now if I print this out, it's been changed. They might have been the same to begin with, but it's an important step. So if we take one of these plots we did before and we want to add link stations on top of it, add another layer, well, all I need to do is add another geom_sf call. Here, I need to tell it what data I'm going to use, and I'm going to tell it that I want it to draw the dots in white. And here we get a lovely map of the tracks with their population and the stations. Same thing if we want to look at the link lines, I'm going to use a second geom_sf call. I'm going to filter down to lines 1 and 2 because the other ones aren't in King County. And then I'm using the scale color manual here to actually color the line best based on whether it is link line 1 or 2. And so with just a few extra lines of code, right, we've added 2 spatial layers into 1 plot. Okay. Now, if you want to actually combine spatial information, not just put it on a plot together, there are a bunch of functions that allow you to compare the spatial attributes of 2 objects. The union would be a common one where if we want to combine 2 data sets of polygons, say we had Washington polygons and Oregon polygons, and we wanted to make them into 1 object. What we're going to go through very quickly in 3 minutes is points to polygon assignment, which is one of the most common types of things you might want to do with ArcGIS. So if I want to identify the census tract that each of these link station lies within, I'm going to use the stJoin function. I'm going to specify first the thing I want to assign to an object. So that's my points to my King County pop. And I'm going to have it return just the first row, since we know that this one has many rows per tract in it. And if I look at the output of this object, this might take a second because that data set's really big. What's going to come out of this at the end is going to be a data set that looks just like link stations, but it's going to pull every column from the first row of King County pop that each row of X lies within onto the data. So it's going to spit out my link stations, but I'm going to now have columns that have the total population and the tract geocode in it. So while that's running, I'll maybe kind of just tell you what's in the rest of the thing so you know. Here we go through assigning points to polygons in depth, and I go through a second way of doing this by hand. So stJoin is convenient. It pulls the data and the attributes from both objects you're joining automatically. Sometimes there's a need to be a bit more specific and careful and actually control that process yourself. And this process for st_intersects can walk you through that. And then the last example that I give that we're not going to have time to go on, which is just, again, another example of a common type of operation, is about calculating distances and some points about if we want to calculate the distance, say, from a light rail station to a census tract, we have to make some decisions about what that distance means. Do we want the point of the light rail station to the edge of a tract, to the centroid of a tract? And what I end up walking you through here is actually using the centroid of a tract to identify the tracts that are within 5 miles of a light rail station, those that contain a light rail, and then making a visualization of that here. Okay. Last thing before we open up for questions, I just want to show you what this object looks like. So again, this is the joined object. We have 1 row for every station. This all looks exactly like the spatial data we downloaded from Sound Transit. But now we have all of these extra columns joined on from the King County pop data set that has the GeoID and has the total population. And then you'll see ones that are missing this information. And that's, of course, because those stations are not in King County. They're probably in Pierce or Snohomish County. So questions before we go away? All right. Well, you know where to find Matt and and I hope our materials can be a good springboard for you as you get more into GIS.
Thanks, everybody. Thanks, Jessica. It's fun.
Bye. Thank you.
Thanks so much.